ship to somebody else.
We come to the next section, and our next speaker is Biao Lian from Princeton University. Please share your screen.
Hi.
So just take
thanks.
place.
Yeah, just 1 second. Can you see the sharing?
We see your slide.
Ah, okay. Okay. Yeah, thanks a lot for the introduction. First, I would like to thank the organizers for giving me this chance of presenting our work. So today I will be talking about quantum chaos of chiral edge states, which is a topic kind of less explored in the past. But I'm glad actually this topic kind of fits well with today's schedule, where simulations and coherence has been talked about and will be also further talked about, I think, in the coming talks. So so this work, this talk will be mainly based on our work done like 2 years ago with Shuaiji Songdi and Zhenbing Yang, where we studied the Chiral SYK model, which actually describes the chaos of the chiral fermions. And I'll also mention about the work currently in progress with Yicheng Hu, who is currently a postdoc in Oxford, where we generalize the ideas to anyons, anyonic edges. And I'll also mention some numerical studies I've been working with Shuaiji Songdi, Duncan Haodan, and Zhenbing as continuation. Okay. So so I will be talking about mainly 2 parts. So in part 1, which is the kind of the main part, I'll talk about the integrability and the chaos of interacting chiral fermions. While in part 2, I will present some current results we have in generalizing the discussion quantum chaos in anyonic chiral edges. So I guess I don't need to introduce the chiral edge states much. Basically, for 2 + 1 dimensional gapped chiral topological phases, they will have protected chiral edge states of various kinds. For example, the complex chiral fermions occur on the edges of integer quantum Hall effects. And the chiral Majorana fermions, which are charge neutral, can occur on the edges of topological superconductor, the chiral one, or particle, or various kinds of fermion states, fermion fractional quantum Hall state, and also chiral spin liquid phases. And we also have more like abelian or non-abelian anyons, which are associated with chiral bosons or more exotic excitations in various kind of topological orders, for instance, fractional quantum Hall states. On the other hand, integrability and chaos are kind of well-known concepts in classical mechanics, and they can also be generalized to quantum mechanics. So for integral systems, basically, the picture is we can predict what is the evolution of the system. And this basically means the model, the system is exactly solvable, and it's robust against perturbations to the initial conditions. For instance, the pendulum, such basically most of the solvable examples in classical mechanics are integrable. And in quantum aspect, a quantum integrable model would have quantum chaos. Would have a quantum coherent behavior. Basically, their evolution would show some robust, for instance, interference phenomena, etc. While for chaotic systems, basically this just means non-integrable. The generic concept is the evolution is unpredictable, and this is more commonly known as the butterfly effect. Basically, the evolution is sensitive to initial conditions, for instance, the weather systems. And for quantum chaos, quantum chaos is still kind of people are still discussing the precise definition of quantum chaos, but basically some feature of the quantum chaos includes the system would easily lose quantum coherence, and also it would show thermalization quickly. And these are kind of related to today's topic. So the chiral edge states, is probably one of the most coherent systems one could find in condensed matter electron systems. And this is actually also the foundations of the recent very interesting experiments detecting anion ratings by Nakamura et al. And Bartolome et al., which they will also give talks just in the coming following. So basically, for instance, in the anion braiding experiment in Nakamura's paper, basically it's important to have coherent interference between the edge states of the fractional quantum Hall states, and this is exactly because these chiral edge states are highly coherent. And this surviving coherence of the edge states actually indicates these chiral edge states are nearly integrable, at least at low energies, under various kind of interactions present in the system. So to understand why the chiral edge states are, there are many examples which are very coherent. Let's look at some examples, simple examples. The first example I'm presenting here is you consider n chiral Majorana modes. Basically, here I use Majorana modes, but you could also consider complex fermions by dividing them into just two Majorana modes. If we have, for instance, n smaller than or equal to 3 flavors of Majorana fermions, then you could try to write down all the interactions these chiral Majorana fermions can have on the edge. For instance, they could have interactions with the bulk phonons, or they could have interactions among themselves, and you would find all the interactions you could write down are irrelevant. So basically, this means at low energy, they behave as just almost free fermions. The other example is the nuclear 1/3 fractional quantum Hall states, which is described by the Chiral Luttinger liquid, which is kind of a free boson theory. And similarly, if you try to write down the interactions, you would find all the possible interactions are irrelevant, including if you allow pairing, it's still kind of irrelevant. So for these above examples, basically you would have free chiral fermions or bosons at low energies, low temperatures, which are integrable. Well, things become a little bit non-trivial when you increase the number of edge channels, chiral edge channels. For instance, if we consider n to the 4 interacting chiral Majorana modes, the theory actually becomes a chiral Luttinger liquid, which is still integrable, but the interaction is doing some non-trivial things now. So in this case, one could have an interaction among all the 4 fermions, which is, if you count the scaling dimension, this is actually a marginal interaction. And a more common way of writing down this formula, this model, is to rewrite the Majorana fermions in terms of a spinful complex fermion. For instance, you write down you define spin up and spin down complex fermion in this way. Then the interaction just becomes a commonly seen Coulomb interaction, local repulsive interaction between upspin and downspin. And this model is known to be basically the Chiral Luttinger liquid, which would show a spin charge separation and is a non-Fermi liquid. Just a little bit more review about this. Basically, the idea of solving the n to the 4 model we just showed is to use the technique known as the bosonization, where we can map the fermions into the bosons in this way. And this mapping actually maps the density operator of the fermions into a linear function of phi, partial x phi. And as a result, one can bosonize the action into actually a free boson action. The interaction plays a role of just a quadratic term in boson action. And this gives us 2 free bosons with different velocities. And the 2 eigenmodes are related to the original boson fields in this way. And the 2 modes actually have the physical meaning of the spin degree of freedom and the charge degree of freedom of the chiral of the complex spinful fermion. So we could also calculate the fermion Green's function which actually shows this interesting behavior, which actually give you the two velocities. And this has been detected actually in non-chiral examples, but basically the physics is similar. One could see these two velocities. So we ask the question then, if we further increase this number of chiral modes, is the low energy integrability still preserved? For instance, we could consider just n copies of chiral topological superconductor, which have n chiral Majorana modes. Then in general, one would have all these marginal interactions among any four of the fermions. And the idea is, so basically, the interesting thing is this interaction is actually exactly marginal, just as in the example of n to the 4, they modify your velocity, and this is independent of the energy scale. So the other thing is, so the number of interactions, as one can see, would increase quickly as you increase the number of flavors. And one could alternatively just write down this as a SON level 1 was weighted model. This is just a comment. So if we look at n to the 5 and the 6, we find the model is still integrable. And basically the way we solve the model is we can consider, we can find a proper Majorana basis by SON rotation of the basis, and then followed by Bosonization. So this is integrable basically for any kind of interactions. You could choose them randomly. So for n to the 5, you have 5 interactions, but we show that by this Majorana basis rotation, you could rewrite equivalent data model as a model of containing just under certain free fermion certain Majorana basis, you could just rewrite the 5 interaction into just a 1 interaction among the first 4 flavor. So this model then decouples into an n to the 4 interacting Majorana model with a free chiral Majorana fermion, the 5th Majorana. So according to our earlier knowledge, this is equivalent to just 2 free chiral bosons and a free chiral Majorana. So it's an integrable model. And for n to the 6, there are 15 interactions, but we show that if you do the proper basis rotation, you could still just reduce the number of interactions down to only 3 interactions. And this then followed by bosonization can show this actually gives you a quadratic boson action, which you can diagonalize to get a 3 free chiral bosons. The only difference is now there's some randomness in the eigenmodes of these chiral bosons, which are orthogonal. But things become interesting when n is starting equal to 7 or larger. So now we have interactions, at least the 35 interactions or more. And what we find is no matter what fermion basis you choose, then after bosonization, you would always get some nonlinear terms in the boson fields. And basically, they take the form of these cosine sine fields of the functions of the phi. So this shows kind of some intrinsic nonlinearity starting from n to the 7 and larger. So this leads us to conjecture actually starting from n to the 7, the system become quantum chaotic and is no longer integrable. And just related to the earlier talks, basically once you show quantum chaos, you would expect these edge modes to show decoherence, and they will thermalize quickly. For instance, if we bring 2 edges together and the number of edge modes is large enough, then you would expect they thermalize quickly, which is chiral. Okay, so the first n to the 7 is actually pretty hard analytically, but easy point we can solve is the large n limit. Basically in this large n case, the model actually defines a model we call the Chiral SYK model, named by Sachdev and Kedav. It's actually a very natural generalization of the original SYK model, which is a 0-dimensional model, into chiral systems. So the model basically now would consider many interactions, but in order the energy, the interaction energy of the system does not diverge, these interactions has to follow some scaling with n. And basically this is what we assume. We assume the interactions can be regarded as random, and the expectation value of j squared is scales with 1 over n to the cube, which is yeah, the same assumption in the original SYK model. So yeah, just to mention a little bit about the original SYK model, it's a exactly solvable quantum chaos model in 0 dimension, containing Majorana fermions, 0-dimensional Majorana fermions, which have Q fermion interactions. And for Q to 4 is the case analogous to the thing here. But the difference here actually is in this Chiral SYK model, this interaction is, again, exactly marginal. If you count the scaling dimension, they actually doesn't flow with energies because of the chirality, the total chirality of the system. The interactions are scaling invariant, and it's important all the way to low energies. And the large n actually allow us to drop some Feynman diagrams and to just keep the leading order 1 over n diagrams. And so this allows us to solve the model exactly using techniques used in SYK literature. And for large n, yeah, if we look at the average, the Green's function of the fermions in the large n limit, at 0 temperature, we find the Green's function looks like this. Which is actually surprising, a little bit surprising that this Green's function look exactly the same as the n to the 4 case, if you remember the result I presented earlier. But the difference now is actually here there's no quasi-particle picture. So earlier in n to the 4 case, there's actually quasi-particle picture that you have free bosons as your quasi-particle. But as we'll show, this system is actually chaotic, and you don't actually expect any pose or things in your bosonic Green's function or etc. That's a crucial difference. So you could also write down the solution at finite temperature, and this turns out to be also the same, exactly the same as n to the 4. Basically, the 2-point function is the same as n to the 4, but not the higher point functions. One thing we could verify first is that the thermal Hall conductance is still quantized in the expected value. This is not that surprising, but just showing that the basically this quantized topological number is robust against the chaos. Yeah, the thermal entropy density can also be calculated. This is another different from the original SYK model. This entropy actually vanishes at 0 temperature, unlike the SYK model, which has a 0 temperature entropy. Yeah, so to characterize the chaos of this model, basically we can look at the Lyapunov exponent of the out of time ordered correlator. So Lyapunov exponent is a concept in classical chaos to characterize the butterfly effect. Basically, if two initial states are separated by a small distance and they evolve as function of time, in the phase space, their position would deviate from each other exponentially, and this exponent lambda is known as the Lyapunov exponent. And quantumly, there's also correspondence by this analog. Basically, we can look at the separation of x as, for example, distance of 2 states at time t with respect to the initial distance separation. And if we convert this into a Poisson bracket and expand it and then convert it to quantum language, then this gives you several terms. And it is shown that this out of time ordered correlator, which has time jumping back and forth, actually gives this, is expected to give this exponential growing behavior of the classical chaos. And quantumly, it is known that this exponent has a quantum upper bound, which is 2 pi over beta, where beta is inverse temperature. So yeah, so basically we calculated the OTOC of the fermions, and as expected, we find the OTOC shows the expected exponential growing behavior as the SYK model. Basically, this correlator, if we look at it along a certain velocity, it would grow exponentially in the 1 over n order with this lambda defined as the Lyapunov exponent along that velocity. And this exponent is actually positive. We show that it's actually positive along any directions between this bounding velocity u minus and u plus, which is basically a causality cone. The causality cone of the model is between u minus and u plus. So this basically shows any information propagating in this causality cone is actually chaotic. And this leading Lyapunov exponent along the leading velocity actually reaches the maximal chaos bound when j is 2 pi. And this is actually the critical interaction strength when the u minus reaches 0, where you start to lose chirality. After this interaction, you would expect some non-chiral deformation of the edges. Okay. Yeah, so in contrast, just to show you that for n to the 4, the OTOC actually is decaying exponentially, which can be solved exactly. Okay, so also we actually studied the level statistics for small n, which actually shows the chaos at small flavors of fermions. So it's known that the if you look at the manic body levels, the neighboring basically the statistics of the neighboring levels, if the system is chaotic, this neighboring level statistics spacing statistics would show statistics reminiscent of the random matrices, basically the Wigner-Dyson distribution given by this function here. While if the system is integrable, the system will show a Poisson distribution, which is exponential decay. And we did a ED study for small n of the Chiral Majorana model. And indeed, we find that, so first there's still a conserved quantity, which is the momentum, total momentum of the system. And inside each of the total momentum sector, for n to 7, we need to see a perfect Wigner-Dyson distribution in the neighboring levels, showing the system is indeed quantum chaotic in n to 7. While in contrast for n to 6, the statistics actually highly degenerate. It's not even a well-defined Poisson due to the high degeneracy of the integrable nature of the system. So this actually confirms our conjecture that the system has a transition from integrable to chaos at between 6 and 7. Okay, now let me briefly talk about the anyonic generalization of these discussions. Yeah, so it's actually similar expectations. One would expect the interactions. So there are certain interactions which could be marginal or relevant in fractional quantum Hall edges, which could also have significant low energy effects. But this is in general only possible when you have multiple edge modes. For example, if we consider, here I just show a simplistic example with an edge with 2 chiral fermion modes. For instance, this could arise from a system of bilayer Fabian state, where you have a bosonic mode hosting a fermion Anyonic statistics. So for this model, basically the free boson part takes this form. Basically, you have 2 boson fields corresponding to the 2 fermions with K matrix 2, which determines the statistics of the fermions. And accordingly, one could write down interactions among these two fermions. And it turns out, so the only non-fractionalized and marginal or relevant interaction one could write down is this one. So this interaction, if you count the scaling dimension, it's exactly marginal. Yeah, it's straightforward. It's just a hopping of charge among the 2 edges, basically. And this model is also actually integrable. It's actually equivalent to 4 free Majorana fermions. And the idea is to, you could define a complex fermion in terms of two complex fermions in terms of these fermion fields. And you could check the scaling dimension actually give you the definition of a fermion. And this maps the interaction actually into a p-wave pairing term of the C minus fermion. So this basically makes the C minus converts the C minus degree of freedom into 2 Majorana fermions. So as a result, starting with 2 fermions, you find adding interactions, you end up with several Majorana fermions and a complex fermion. Of course, here the original degree of freedom is still fermions. So, but this actually allows us to calculate the fermion correlations, which turns out to be this form. It's actually a factor like this multiplied by the fermion correlator. Yeah, so this is an integrable example. So in general, for a class of Abelian chiral modes with charge conservations, yeah, actually, we could show that the above conclusions kind of, there's a kind of a general conclusion that the correlation of a chiral Abelian anyons can be, yeah, of some scaling dimension, can be calculated in terms of some fermion correlators. Yeah, basically there's in this case, there is generically a way to map the model into some kind of fermion models. So if there's no interaction, then these, you would expect the chiral Abelian anyons to have a scaling dimension, yeah, to have a scaling correlation like this with this scaling behavior determined by the scaling dimension. Well, if you have interacting correlation, the correlation between the anyons actually become a factor like this multiplied by correlator of fermions. So the correlator of fermions has a scaling scales with 1 over x. So this still have the same the same scaling dimension, scaling behavior as the free case, but this fermion part could involve either chaos, could involve chaos actually if the interactions are sufficient. Yeah, so similarly, the expression generalized to endpoint functions. But one thing interesting to note is that if you exchange these two correlators, you still get a 2 pi delta statistical phase. So it's kind of the anyonic statistical phase remains robust, but decoherence could occur if the system is chaotic. So one of the future questions is how the interacting edge correlations could affect the anion braiding and scattering measurements, like recently done in anion braiding detections. So yeah, lastly, I just want to present a solvable chaotic model, which is also involves some large and limit.
Biao, can you finish your talk in
I'll finish
3
in
minutes?
Yeah, in 2 minutes probably.
Okay, thank you.
Yeah, this is yeah. Okay, yeah. So the if we consider n copies of SUM level 1 West-Sumino model, Witten model, basically is described by this formula. So basically, this model could contain some interactions among the SUM spin currents of different copies. And the earlier n equal to 2, earlier Samian model actually is an example of the n equal to 2 and m equal to 2 of this model, which is actually integrable. While for large n and m, this actually is exactly the chiral generalization of the original SYK model proposed by Sachdev and Ye, which is actually a spin SUM spin model. But this difference is here. Here, this model actually contains anyonic excitations with these scaling dimensions, and by mapping these currents into a fermion picture, actually this requires you add some ancillary fermion degrees freedom. You could map this model into a complex chiral SYK model, which actually have the same solution as the the Majorana one I showed earlier. As a result, so by earlier conclusion, we can actually calculate the anion correlators, which is of this form. And the OTOC of these anionic excitations can also be calculated. Then they actually also show the quantum chaos, as similar to earlier. So the expected picture is, again, as the number of degree of freedom increase, the edge channels increase. Precisely in this model is n and m, you would expect a transition from integrability to chaos. Okay, with this, let me conclude my talk. So the basic message is, you see actually when you have multiple edge modes, actually quantum coherence could lose due to the chaotic nature of the edge states. And this might be essential for the thermal equilibrium, which Dima mentioned. Although here it's a purely chiral discussion actually. And also the interference experiments, if we want to look at fitting factors higher than 1, etc. With more modes. Okay, thank you.
Okay, we have time for one quick question from Berg.
I just wanted to ask, if I understand what your calculation, you're assuming that before you turn on the interactions, all the velocities are the same. But in practice, of course, if you have many modes, they might have different velocities. And in practice, if they're very different, of course, you'd be very. Can you tell us what the effect would be if they're only slightly different or quite different?
Yeah, very good question. Actually, we are actually exploring that numerically now, because if you have varying velocities, actually the problem becomes analytically very hard. So for n smaller than, for this Majorana model, actually, if you increase, if you add velocity and anisotropy in the system, at least numerically, you will find for n smaller than 6, the model also start to show quantum chaos. Actually, in a level statistics sense, but there seems to be some adiabatic change when the velocity and anisotropy becomes large enough, much larger than the interaction scale, then it starts to recover the integrability, but in a different way. Basically this is still under study, but but indeed the velocity and anisotropy also have an important effect.
Okay, so thank you very much for a very nice talk. So we go to the next speaker.